So as I swing this, if I let go, which way will it go? So let's be more specific, or change it a little bit. If I'm standing here and I swing this around, where do I need to let go of it so that it hits the X? It's basically just off center on that one. So if we picture this is the classroom, there's the X, I'm standing here, swinging this around like that. And just for the sake of ease of conversation, give it to me in terms of time, so 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock, and then 2 o'clock. If somebody says I have to release it at 5 o'clock and someone says 4:59, I can't differentiate between those, so probably half-hour increments. So at what point do I release it? I heard a 3, I think. Right. So one says right here.
Which way is it turning?
It's spinning this way.
Kind of like 1 or 12, but like straight at it.
Straight? Okay, so somewhere around here.
Yeah.
Okay. Anyone else? Place your bets. All right, so let me do the, so I was saying about here, looking at that right there. If you're nervous, you can move, but I will say that if I felt like I was going to hit you with it, then I would ask you to move.
Thank you.
All right, so I have to do it slowly enough so I have some control. So, Brewer, you were suggesting what is right between us?
Yeah.
Okay. So 1, 2, 3, go. Did I release it at the wrong time? All right, so that didn't do it. Now, if I could spin it faster, I would, but the faster I spin it, the less control I have. So then there was 3 o'clock, and then 2 o'clock. So just all right. So here's 3 o'clock. 1, 2, 3, go. And it was about like that. So when I release it, which direction does it go in? Which would be in terms of the circle? So if that's my circle right there, if I release it at this point, which way would it go?
It's along the tangent line.
All right, louder please.
It's along the tangent line.
Along the tangent line, so like it would go that way?
Yeah, about that way.
Is that what you were suggesting, Kenley, or were you thinking that you picturing that?
I was picturing that.
The curve?
Yeah.
All right, what is Newton's first law of motion?
An object in motion will stay in motion.
Okay. Newton's second law of motion? You've seen it. That's the one. Yeah. Basically, Newton's first law of motion is just Newton's second law of motion. Well, for me, Newton's second law of motion is succinct, and it covers not only Newton's first law, but everything else. So let's talk about Newton's first law of motion there. Do you want to give me the whole thing? Okay. Anyone want to give me the whole thing?
Things at rest and the state at rest? Is that like the last one?
Yeah, and
Things are much. Oh, wait, no.
Most action on my house.
Oh,
yeah, that's a critical piece right there. So there's one other piece that's sort of implied but not really spoken, is the fact that the object will maintain its velocity. So an object wants to keep doing whatever it's doing. And I know I do it in one of the videos, but let me do the inertia girl story. My daughter, when she was young, my wife and I both called her the inertia girl, because whatever she was doing, she wanted to keep doing. We needed to go to the store. She was too young to leave by herself, but she didn't want to go. We get to the store. She doesn't want to get out of the car. We get into the store. She doesn't want to leave the store. Whatever she was doing, she wanted to keep doing. She didn't want to change. Thus, inertia girl. That is a really annoying sound. You know, there's certain advantages to hearing loss, but the fact that I can hear it. All right, so an object wants to keep doing whatever it is doing. So whatever velocity it has, or whatever, whatever velocity it has, it wants to maintain that velocity. So objects, black on black, here we go. Objects want, that implies a certain thinking process. Objects tend, I'm going back to want to maintain velocity. That's magnitude and direction. And this was a huge departure from historically the way it was thought of, that if you think back to Aristotle, objects wanted to be in their natural position. Solid objects fall because solid objects want to be down. Gases rise because that's where gases are supposed to be. In essence, the whole Aristotelian view was to look at density. But the departure was that the objects don't want to be in a natural place, they want to do whatever they are doing. So if a car is moving at 100 miles an hour, it wants to maintain that. And if it doesn't, if any object does not maintain its velocity, there has to be some influence that causes it to change. In other words, if there's a change in velocity, that means there's an acceleration, and by Newton's second law, that means there is a net force. Thus, when we talk about equilibrium, and we say that equilibrium means acceleration is zero, which means that the change in velocity is zero, which means that the total force is zero, those go hand in hand. If one is zero, they're all zero. So I actually could put arrows going in both directions. There's an example in the book that we use for Physics 110, and it bugs me, not enough to change the book, but the author calls inertia basically a term for laziness, and that's a mistake. If you're digging a hole, laziness says that you're going to stop as soon as possible. Inertia would indicate that if you're digging a hole, you're going to keep digging until something makes you stop. So inertia, you want to keep doing whatever you're doing. Or in terms of physics, whatever velocity you have, you want to maintain it. So, back to this. If I have an object that is swinging, from our point of view here, counterclockwise, why does it travel in a circle to begin with?
because the string is keeping it from moving outward.
And what force is that?
Tension.
Yeah. So if we did a force diagram here, we have tension pulling it inwards. Now I'm going to ignore the gravitational force at the moment because that would be into the board from our point of view here. So once I let go of the string, what happens to the tension?
There is none.
Yeah. And without that tension, the object will then maintain its velocity. It's this outside force that's causing it to go in a circle. It wants to go straight, but every time it tries to go straight, something just keeps pulling it back in. And I think ultimately in Godfather 3, that's the reason why that line was put in there. It has nothing to do with the plot line, but it was a subtle physics thing. I'm sticking with it. Just like the physics reference in Princess Bride, which I discussed in the next semester course. So, it will travel in a straight line. It will not curve because there's no reason for it to curve. There would have to be it's going to travel in one direction unless something causes it to curve. So that's not going to happen. Again, unless there's something causing it to not go in a straight line. Now, when I released it, it did not go in a straight line. It did curve downwards because there was an outside force of gravity, causing it to fall. Other questions before I erase? All right. I know what you're thinking, as usual. All that's well and good, but where's the math? Well, let's do some math. All right, so I have an object that's traveling in a circle. And let's see, that's roughly the center right there. We'll make that straight. So at some point, the object is here. It's traveling in that direction. That is the initial velocity. And then at some other point, it's traveling there. The final velocity. I'm just going to label this angle here phi. So I'm looking at, I got the vertical right there, and I'm looking at two moments in time with the same, well, both the same arc length from the central point. Let's establish our convention, I hat and j hat. What's the formula for acceleration? The other one, the chapter 2 version.
Change the velocity of the time.
And change in velocity, how do you find that?
V to the final velocity minus initial velocity.
Over however much time it takes to get there. We will assume that the speed is constant, so shorthand notation, the magnitude of VI is equal to the magnitude of VF. Those V's are both supposed to be lowercase. Now, if I'm subtracting one vector from the other, I need to somehow figure out how to do that. So what we're going to do is we'll break it into components, or decompose it as I call it other times. So if I'm looking at my structure right here, this angle right here is phi. I know this is perpendicular to it. That has a magnitude of V. So what I want to do is figure out what is that angle right there. Well, let's see. I know that is a right angle. I know that is a right angle because I'm breaking V up into horizontal and vertical components. If this angle here is phi and that is a right angle, what would this angle here be? And for those who are looking now, I'm talking about this angle right here. If that's phi and that's 90, what is this? You said 180 minus.
Like the right angle plus phi.
Okay, so 180 minus the sum of those?
Yeah.
No, yeah. So this one, so mystery angle would be 180 minus degrees, minus 90 degrees plus phi. So which ends up being 90 degrees minus phi. It's the complement. So I'm going to label my complement as phi prime. So phi plus phi prime is equal to 90 degrees. Or for the cool people, pi over 2. I know this is a right angle here. And we can go for stunning visual effects. Ooh. That's a right angle. I know this is phi prime. So this angle right here must be phi, because the sum of these two has to add up to 90 degrees. So the angle VI makes with the horizontal is the same angle as this down here. Therefore, I have VI, or some magnitude V. This angle here is phi. And so I'm breaking it up into its components. So V initial is equal to V cosine phi I hat plus V sine phi j hat. Dramatic pause for questions.
I in this case would be the same as theta and the things we've done before.
Yes. Yeah. Phi and theta are the two angles that are typically used, or the two symbols that are typically used for angles. Alpha, beta, gamma are probably the next set that are typically used. But what symbols should you never use for an angle? Yes. Despite that one textbook that did it. All right, V final, well, you can go through the exact same thinking process, but V final, this angle here would also be phi. So so this was my V initial. V final, it's now pointing into the fourth quadrant. This angle here is phi, and we would break it into components. And so V final is V cosine phi I hat minus V sine phi j hat. So plugging into my formula there, my acceleration would be my final velocity, so V cosine phi I hat minus V sine phi j hat minus V cosine phi I hat plus V sine phi j hat. Divided by time. And what does that simplify into? Did you say one of J hat over T? Yep. Distribute the minus sign, the cosine terms, the I hat terms cancel out. So I have a formula for acceleration based upon speed. Trouble is, I got that sign of phi in there, so I need to somehow deal with that. So what I'm going to do is phi is somewhat arbitrary, but I want to make phi as small as possible. Because I really want to figure out what is the acceleration at this point right here. And so I really should make phi so that VI and VF are really close to each other. Not on the top of each other, but what's termed in math, infinitesimally close. So let phi be small. So I have my phi is if you have the two less than symbols, that means much less than, so phi is much less than 1. Now notice I didn't put any units over here. If I don't put units down, what are the units of the angle?
Radian?
Yes. So it's an implied radiance here. And what is a radian? Besides a unit for an angle. I assume some people in here have had some drink. I appreciate you making eye contact. Well, actually, both of you making eye contact. It looked like there was some avoidance. All right. The bit on radians. Let's talk about the Babylonians. We'll come back to this page. Babylonians felt that the number 60 had some special meaning to it. They had a base 60 system. Now 60, in using our notation, 60 actually is a nice number because it is divisible by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and 60. There are a couple of numbers